Thank you very much, everybody, and good afternoon or good morning, wherever you are in the world this morning. So my name is Juri the Rooster, and alongside my colleague David Catto, we're talking to you today about how to solve some of the challenges within the EV test field. Okay, so if we set a bit of a context behind the scenes, or a bit of a, how would I say, a description of the landscape as we know it. You know, the electric vehicle industry is an exciting and rapidly changing environment. There's been great change over the last number of years, and with these changes, we've seen a lot of impacts happening within the market. So, you know, a few of the changes we've seen, or the impacts that we've seen, is that cars need to be safer. There's new technologies rising. Government legislation is pushing for greener footprints, and vehicles obviously need to be brought into the market at a quicker cycle. This obviously means that there's more pressure, specifically within the R&D environment or the V curve, as well as the production environment. And the reality is, not only are OEMs going to feel the heat, but this is also going to be felt further down the chain. So we're talking about tier 1s and tier 2 suppliers here. So what does this actually mean? What is the actual impact of these challenges? So the implications are far more reaching and critical for OEMs and the supply chain than meets the eye. You know, if we compare sort of combustion engine versus electric dyno speeds, for example, in the combustion world, we were talking around about 5,000 to 8,000 RPM range, where in the electric side, we're literally talking 21,000 RPM all the way up to 27,000 RPM currently. And who knows, maybe that might even increase in the future. And I think the reality is also a simple statement like, oh, you know what, we just need to change the dyno speed, right? How difficult can that be? These things actually have huge implications. You know, obviously there are mechanical parts that need to change. However, an entire DAC and control system, as well as the analysis equipment, needs to change so that we're actually able to accurately produce results within the test environment. And obviously, as these tests are taking change, we are seeing the following trends in the industry. You know, there's a greater need for adaptability. The test requirements are completely fluid. Budgets are relatively stagnant, you know, and we're still having to achieve these results with the same resources. And the reality is also that we've got operators and we need to get solid and reliable test results that we need to hand maybe today or tomorrow or next week to actually analyze. And I think the reality is this is not an easy challenge, yet somehow we need to overcome this challenge. So obviously we have this sort of landscape, we have this challenge within mind. So from our perspective, how we've sort of tried to sort of tackle it is we've developed an advanced software platform to address many of these needs. Now, this has very much been in conjunction with customer input, and there's been a lot of back and forth with customers. We obviously come more from a systems integration background. So, you know, we've worked with a lot of customers within the automotive industry. We understand their pain points, and we've really taken that on board to build a framework, as we would call it. And this framework effectively consists of two parts. Firstly, there's a commercial off-the-shelf electrical hardware platform, and on top of that sits a flexible software layer. So this obviously means that there's flexibility, but it also provides a lot of control to you as the customer. So that gives us a bit of a high-level introduction. Some of the application spaces we're very much focused on and where we're excelling is obviously production as well as the validation space, more specifically around the two-wheel drive and the four-wheel drive e-axle testing, you know, the classic spin rig test. And obviously, if you're not doing spin rig test, you might want to be doing some back-to-back testing. With regards to the battery side of things, there's obviously cycling as well as the normal testing. And then we also have motor emulation. And we were specifically covering a multitude of application spaces so that there's a synergy across departments where organizations actually need it. So if we look a bit at the actual sort of like top level approach that we've taken with this framework, If we look at this, let me just get my laser pointer here quickly. If we look at this framework, like I said previously, there was a lot of discussion with customers, and there was actually a lot of talk about, open versus complete solutions, because as a customer, those are your two choices currently on the market. And, based on obviously where we've come from as a systems integrator, we've always been a proponent for the open solution. And a lot of the feedback we got from customers is that, yes, an open solution is great. However, the reality is it is very time consuming to get off the ground. And there's also quite a bit of time to actually keep it up and running. So based on all these points, we've actually decided to develop a software layer that's a bit more like an abstraction layer versus a standard software layer. And you actually interact with this abstraction layer so that it's a lot easier for you to sort of run your test cells or test applications. So what we effectively have, or how the system is broken down, is there's like this test management user interface, which sits at the top. So that's where you'll be interfacing with the system. That's whether it's an operator or an engineer, or admin user. And this is effectively, sort of where you'll be writing your tests, cell control, collecting data, etc. So below that, we've got what we would call a test management layer. So within that layer, we have a test engine. There's some alarming, there's limits, there's models, there's hardware mapping that sits within that layer. Below that, we've got a software and hardware interface layer. So that's effectively where, your plugins or some of your drivers will be sitting, where you'll also be sort of doing some system deployment, as we would call it, and also mapping out some of your hardware. So all of that has largely, or the first three layers have effectively been very much software defined. Then all of that sits on top of a commercial off-the-shelf hardware layer. So this consists of a real-time controller. There's some remote DAC control signals as well. And obviously we have some communication interfaces. And this is really important because obviously the signals and these comm links is what interacts with the actual sort of instruments or devices within a test cell. So that's, whether it's power analyzers, battery cyclers, your safety chain, simulators, etc. That's how you're going to be interacting with the cells. Okay. So obviously, as I said previously, there's a lot of pressure within the electric vehicle landscape, specifically around resources. We've seen that a lot of customers either need to reuse existing equipment, they have a mix of equipment that they want to use, or they don't necessarily want to be locked into one supplier or a black box solution, if you will. So obviously with this in mind, I'm sure everybody's heard, Monday morning comes and you're sitting in a meeting and somebody goes, oh, we've got this test we need to run. Can I just add, I don't know, like 4 more thermocouples? Or, we've got this swanky new power analyzer. How can we actually use this device, right? It's got a comms port. All you need to do is sort of just like plug it in and then you go, right? But I think the reality is if these signals or devices aren't already incorporated or integrated into a closed or black box solution, there is a cost and there is a lead time to actually getting this kit up and running or sort of adapting to these new test environments. So based on this is why we've gone for that commercial off-the-shelf hardware solution that I mentioned before. This obviously enables you to add different signals and COM cards, so you can add different instruments and signals based on your current and future requirements. Okay, from a high level, the base clock speeds are around approximately 1 kilohertz, and we're also able to do burst sort of speeds of up to 200 kilohertz for the data acquisition side of things. With regards to the comms protocols, we're able to implement a number of different solutions, anything from sort of the CAN environment all the way up to RS-232, depending on what you require. Obviously, to make it a bit easier, we've built what you would call a plugin template. So if you need any sort of specific use cases that you need to have a general instrument in, you can use the plugin. Or if there's anything else you want to add additionally, or you want to build in your own functionality, we've even given you the ability to write your own driver set for that. Okay, so move to the next slide. So with that, I'm going to hand it over to Dave, who will give a bit more insight into the nuts and bolts of how this works.
Great, thanks, Juri. So my name's Dave Catto. I kind of head up the software team for Austin Consultants. So let me jump in and with this slide, which is a kind of view on our evolution software, let me give you a bit of technical context here. What you're seeing here is one of the plugin pages as it's kind of loaded into the system. For certain types of testing, there are the components of a test cell that'll always be there in order to do the testing that you want to do. We call these simply standard devices. They're standard for the kind of tests that you want to do. For example, in an e-motor testing cell, the evolution system has already been told that the e-motor testing is the kind of testing you want to do in this cell, and as a result, it expects to have a number of standard devices. One of these, for example, being the dyno. You can see on this slide here, this particular plugin being brought in is an ABB inverter communicating over CAN open. In fact, this particular customer had a fairly old legacy equipment that needed to be integrated into the control system. They didn't have the budget to replace huge dyno equipment, but it was using the industrial standard CAN open protocol. So it was very quick to write a plugin to this equipment. And plugins, as you just said, is something that customers can write themselves, and we provide templates to do this. The plugin abstracts all the ABB specific communications and translates that into information and channels within the evolution system. Any of these standard devices must implement a minimum subset of channels, like for a dyno example, the speed set point or the mode of operation, speed or torque. The interface can have as many extra data channels on top of that as you like, but it must have this minimum subset. The core channels must be covered. Why is that important? I mean, this information is important for a couple of different reasons. It means the evolution knows where certain pieces of information are and how to get at them. And as a result, we can provide pre-mapped UI components, or widgets as we call them, just ready to use and saving the operator time in mapping controls to certain channels. I guess you can kind of think of these standard devices as an abstraction layer. It also means that if another cell that you were using has a different dyno, maybe from somebody like Unico or another manufacturer, you'd not see any difference when using evolution, apart from this plugin piece, which is something you write once and use again. The core interface is the same, meaning that you can write tests, and if you write tests, these tests, once proven, could be reusable between test cells as well, even with different dynos or different battery simulators. This sharing of proven tests to a public area and across test cells is also built into the evolution system. Juri, let me hand back to you for the next slide.
Cool, thanks, Dave. Okay, so we obviously have this COT sort of hardware platform, but how, we got devices that are sort of communicating with it, whether that be DAC or on the more the sort of comms protocol side of things, that how do we actually go about sort of, how would I say, controlling it or implementing it within the system. So effectively what you need to do from a high level is you first need to set up your devices, instruments or signals that will be sort of allocated within a test cell. And I very much want to stress at this point, we've worked and collaborated a lot with customers on the actual workflows within the framework. Okay, so the whole idea here is that the users will be guided through a step-by-step workflow, and this is very much been by design. So through this process, there will be a number of steps that will be performed. This can be anything from scaling and calibration all the way through to limits and alarms being set up. But at the end of this setup, the reality is that you'll be sort of ready to deploy from a hardware perspective, and that no sort of steps might have been missed, or that the system might, act in an erratic way, etc., because all the steps need to be completed before you can actually deploy the system. Okay, so I'll hand over to Dave again.
Great, thanks, Juri. So this slide again is another view of the evolution software. It's a view of the transition from that area where we've been configuring the system, where you want, how you want your system to look like, which channels you want to have access to, And we're moving into a kind of running or operational phase at this point, where signals and systems become live. Just before we enter that stage, at this point, we have access to any of the channels that have been set up in the system. And the system is asking us here in this page, as an example, whether there are any of the channels that we want to log in a background log. Of course, that's one of many of logging options that you can also change once running. But this is kind of the background log, which is run all the time. And you also have access to set up alarms on any of these channels. The whole point here is that any channel or any data coming into or out of the system is just a channel, and any channel can have alarms and limits set on it. The alarms, they have upper and lower warnings and limits, so you can be warned when you're getting close to that limit, and these can be dynamically inhibited or uninhibited during running. This is important for things like coolers that need a minimum flow rate, but obviously starting from 0 flow rate when the system comes up, you don't want to be alarming all over the place. And these alarms and logging selections are saved for next time you're running, so you don't have to set up each time. The whole overall workflow is safety-centric, and consistent alarms and limits flow throughout the whole system. Admin limits not set on this screen, but via a permission system, can never be overridden. And all of the set points go through safety models before they actually go out to the hardware. As we see here, operators do have the ability to define a working set specific to the kind of testing that they want to do. Certain alarm limits, certain levels, certain things running and certain things not. If the administrator decides the system must not exceed 20,000 RPM or 700 volts on a battery, for example, the operator cannot override this or accidentally breach these kind of limits. Back to you, Juri. Oh, okay, this is for me too. Apologies. So this is another view into the system. This is where we map channels together. So as I said earlier, it's really important that we can bring signals into the system and also be able to control values going out. But the evolution system has the ability to do a form of processing in line with this data. Get the data in, process it, and get it back out to the real world. And it's a core part of a lot of testing these days. In evolution, we call this processing in the middle models. We'll talk more about these and the capability of bringing models into the system in a few slides' time. But here I want to focus on the ability to easily map parts of the system together. Using the filters on the left, we can show parts of the system and hide other parts of the system. And here, as an example, although not really a real-world example, an analog input from the real world being measured by the DAC system is mapped to the break input of one of these models. This torque demand model at the middle of the slide. The input is mapped to the input of the model. There's some processing done inside the model, and then the output of the model is a torque set point, which itself is then mapped to the dyno mapped torque set point. So this visual understanding of how the data is mapped together is a really important way of the system being flexible to new requirements, but also being clear as to what is actually linked together and what's actually happening in your system.
Cool.
Juri.
Thanks for that, Dave. Okay, so obviously as an organization, whether you work in the production test environment or the validation side of things, you're always going to have a team of people working sort of with your resources or on your resources, or maybe multiple sort of teams or departments. And the reality is you're going to have different skill sets, different people, and these different people with their different skill sets are going to actually have to perform different tasks within the system. So what we've decided to do is take an approach that we're going to supply a matrix-based configurable sort of user access, if you will, right? So this gets set by the administrator within the system. This obviously means that your operator can have different rights, for example, to like a test technician, whereas maybe you want the people who are writing the tests to actually only be able to sort of write tests and not deploy hardware configurations. So all of this is very much accessible and you're able to set that within the system. And the whole idea behind it being that you as the customer have control over what you're doing and who's doing what within the system. Okay, so obviously what's happened is you have your hardware set up, you've got your users in the system, but how do you actually go about writing a test, right? Because this is actually some of the core functionality that you require as a customer. So with this in mind, we generally have two options, the first being a built-in test sequencer, and the second is a Python scripting tool. So if we first look at the built-in test sequencer, this is a very sort of basic tool, and it's more built for around basic sort of sequences that need to happen step by step. Ideally for more simplistic tests or more sort of rapid tests, if you will. For more complicated tests and more intricate tasks, we definitely recommend the Python scripting tool that we have. So we've got a fully built-in Python library within the framework. And the reason for why we've gone with Python is because we've had a lot of feedback from customers that Python is a dominant skill set currently within the market. So whether you're sort of an existing engineer or a new engineer joining the world, you generally have that skill set. So customers like the fact that people are able to sort of use Python within the system. So with that, let's have a look at what this Python editor actually looks like. And with that, I'll hand it over to Dave.
Okay. I don't want to scare people off with delving straight into Python, but I kind of want to talk about this because how to write and run tests is a key differentiator for evolution in this space. Things are changing so rapidly in the EV market that testing requirements are always changing, as Juri said earlier. As Juri said, we do have the real-time sequencer, but this is a functional testing with a get channel, set channel, start a log file kind of test. However, with the best will in the world, we are not going to be able to provide enough test steps in that sequencer to cover all of the strange and evolving tests that our customers will want to do. Although we'd like customers to come back to us, we don't want to make them come back to us. So our open approach to testing to provide fully featured Python interface is to provide a fully featured Python interface to write these tests. As you said, Python is by far the most popular scripting language and actually the most popular programming language in the world currently by a long way. But you don't need to be a programmer here to use the evolution system. We're really using it in its most basic scripting form. As you said, what it does mean is that for your recruiting of engineers, it widens your net for bringing people in to run the test system. A large portion of engineers have come across Python either during their training or even tinkering at home on hobby projects. So what do we run? We run a full Python 3 environment here, so engineers can enjoy access to free analysis libraries like NumPy and Pandas. We also have integrated the tests into Evolution, an integrated development environment into Evolution, so that we can provide extra facilities like checking whether the channel that you're trying to access is available in the configuration that you have. We've also integrated the testing in so that once a test is written, we can parse the test and actually bring out the tests from within the script. As you can see here in the bottom right-hand side, it's parsed the text and brought us a number of functions, cleanup, DCIR test in this case, and a main function, which allows you to, once the test is written, actually not even look at the Python, but call the tests and parameterize the tests, i.e. change the parameters that are going into the tests. A lot of our customers set up potentially a quick test to check the test is working, and maybe another set of parameters, which is the full 3-hour test, for example. Python itself is very, very easy to understand. It's slightly more structured, but essentially pretty much English. So the scripts themselves are very readable. The interface to the test system is just a single import library at the top of the script, with a very easy to use and fully documented API, with more things than just get and set channel, but also ability to set dyno speed, set talk set point, that kind of thing. And to add to that, we've also had people that have never seen Python. We've had them up and running with fully functional tests in a matter of hours. So we're quite confident in the flexibility of this way of testing the system. Back to you, Juri.
Cool, thanks, Dave. Okay, so obviously what happens is, and I guess maybe this is the intricate part or the juicy bit for customers, because the reality is you obviously have your test sequence written. Now it's actually time for the wheels to hit the ground running by starting a test and collecting data, right? Because that's actually what you're after, right? You want that data to be able to analyze it. So what we've done, and this is once again key, has been customer feedback, right? We've created a user interface that will allow you, the customer, to decide what information you want to see. Effectively, what we've got a number of sort of tabs within the system. And within each tab, you're able to define what sort of information you would like to see. We have defined a widget, which is a way to create a UI element to display information from a specific device or a number of map channels. So if you would like to display torque input signals alongside power analyzer and inverter data, you're able to do this all in one tab. This flexibility within this framework ensures that each screen tab is built around your test requirements. As you can see in the picture here, let me just get the cursor here. So we obviously have, like, for example, a fluid conditioning unit in the screen here. We've got a battery simulator and we've got a dyno. So based on this customer's requirements, this is some of the information they wanted to see. They populated the screen themselves as they thought, this is the information we want some of our test operators to see. And at the top here, you'll see these are the tabs I'm talking about. So based on the different tabs, you're able to sort of like add different information on that. And Dave, on the next slide, will give us a bit more detail around that.
Yeah. So this is just another tab, and this is just some slightly different, more UI components or UI widgets, as we call them. This is a different customer view, and they decided that they want to see speed and torque mapped against time. The tabs are completely configurable, and each user and each test, as Juri said, may have different requirements. There are 4 widgets on this screen, as an example. They've been pulled in and sized based on what the customer wants to display. To give an example, the top left is a slider view on individual channels. It gives a visual representation of instantaneous data to the assigned channels. The operator has assigned a certain channel to each of these, and they also have the alarms. So any channel can have an alarm, and the alarm's integrated into the display here. So the alarm levels would be the orange and the reds. It gives you a very quick and easy indication as to whether some of your channels have gone into their alarm state. If there is a full-on alarm, then actually the top and bottom bars go full red, so it's very easy to see. But this gives you an idea of some of the non-critical flow rates are getting to their warning levels. Below that is a simple table view. It gives you the ability to quickly access, at a glance, a lot of the data. Obviously, all the scaling and calibration and units are all taken into account and visible at this point in the system. On the right-hand side, we've just got 2 graph widgets, both standard graphs, both plotting data over time, but with multiple selected channels on each. There are many other widgets to choose from. Many, and some of them specific to the dynos, some of them specific to power analyzers, but many other tables and graphs and views.
Cool. Thanks a lot for that, Dave. So another sort of intricate part of the system or functionality we decided to build in is we wanted to add some models, if you will. And I guess this applies more to the validation environment. But I think the reality is more and more there's a requirement to run models within validation tests, right? If we look, for example, at the OEM environment, and why modeling is used a lot there is because on-track testing is only getting more expensive. And being able to reduce on-track testing means that not only is there a saving in money, but also there's obviously a saving in time. But you're also actually picking up sort of problems and understanding what's actually going wrong with the product before the testing actually takes place, right? And the reality is, it's not even just OEMs that can benefit from this. It's obviously, tier ones, tier twos. If you're able to sort of go through that, catching a problem early, then iterating on the product and then testing the product again, and then sort of running through that again and refining your product, and then sort of going to a more pre-production sample, if you will. There's obviously a huge cost and time saving on that. So I know Dave has got a few words you'd like to share about modeling.
Yeah, exactly. So the ability to run models opens up many possibilities, including things like dynamic profiles or dynamic alarms. Dynamic profiles is reacting to a situation rather than pre-baked profiles or pre-baked data points. Dynamic alarms would be potentially a changing alarm level based on a set point of a system. As we said before in the mapping slide, a model can be anything from a simple bit of processing, maybe a filter on a channel, up to a full, potentially a battery model, for example. With model processing in the loop at 1 kilohertz, really the world's your oyster. It opens up prototype testing, running algorithm testing in a safe and managed environment in a test cell, or even things like torque biasing or other dynamic control and measurement and testing. Many environments in which you can build the model, some of these are listed on the slide here, MATLAB, Simulink, LabVIEW, from all the way down to C, raw C code, allows many people, even outside the testing environment, maybe people from R&D, to reuse the testing system for their work as well. Back to you, Juri.
Well, thanks, Dave. And then I believe you want to talk a bit about sort of versioning within the system, Dave.
Yeah. So this slide is really showing the components to the evolution system. So the libraries really are components in the system, and each one of these sections has its own versioning. One of the things that we've come across over our experience in this field is that getting back to a test that you did 6 months ago is really quite difficult, certainly when people are changing things all over the place. So each one of these areas, plugins, models, CSV profiles, is all managed in a library. And when I say managed, I mean fully version controlled, so that when you have that requirement to go back to 6 months ago, you can actually get there with a configuration. Previous to Evolution, we've spent many years as an engineering consultancy helping people with their test systems, and Evolution and its features have really grown out of that real world demand and seeing where things go wrong and how they can get out of hand. And we've tried to manage that with the features built into the system.
Thanks, Dave. So I think lastly, I just want to talk a bit about test cell safety. So, I know test cell safety is something that can sort of easily be overlooked when a test cell is being defined or revamped or built, if you will. And the reality is why test cell safety is important is generally two reasons. Firstly is obviously the human factor, but secondly is actually, you need to be able to protect your DUT or UUT or the product that you're trying to test. So obviously when it comes to people, there's like e-stops, interlocks, etc. But when it comes to the product side of things, if we take, for example, a dyno rig, you might have a chiller hooked up to it and you need that chiller to run, because otherwise you're going to be damaging the cell or even the device that you're testing if the chiller isn't actually working properly. So with that regard, it's very important to be able to see and have an integrated system when it comes to your safety. So you want sort of one view for the operator to know, yes, you know what, everything is clear. I've got the all green lights. I can run the system. From our perspective, we can obviously help design and build safety systems based on your requirements. But if you've already got a safety system or you've got a different vendor you want to go with, we're more than happy to work with them and then integrate that into the system. But at the end of the day, we want to make sure your signals are coming through our system and you're able to see it from a live view. Great stuff. So thank you very much for your time today.